Back in Chapter 5, we spent a little bit of time multiplying binomials that looked a little bit like this. This is a very simple example, but it'll get the point across. I told you then that although it's a special case, there's no reason you can't just do normal distribution. X times x is x squared. X times negative 3 is minus 3x. 3 times x is 3x, and 3 times negative 3 is negative 9. Combining like terms, I get x squared. These cancel each other out, or add up to 0, and then minus 9. This is called the difference of two squares. Notice that the result could have been achieved by simply writing the first thing squared minus, and that's important, the last thing squared. So one way to factor a polynomial that's the difference of two squares is to undo this process. Working backwards, I have x squared plus 5x minus 5x minus 25. The common factor to both of these is x, and the common factor to both of these is negative 5. Remember, we bring this sign down, and then I'm undistributing a negative times it needs to be a positive to get me this negative. What's common now is x plus 5, and what's left over is x minus 5. As with multiplication, if you can look at this and recognize the form and jump straight to this line, as long as it's right, then that's fine. You don't need to do any of this other work. That's true here as well. If you can look at this form and jump straight to this line, that's also fine. Again, as long as it's right. But what happens if you get a harder problem? For example, what if you're asked to factor 16x squared minus 25? Can you see this as 4x all squared minus 5 squared? If you can, then you can jump straight to here is its factored form. And if you got that, that's great. That's all you need to worry about. But if you didn't, here's another way to do this problem. You've actually already done it in the previous two sections. All we have to do is rewrite this as a trinomial. It's only got two terms in it, but that doesn't mean we can't introduce what I call a zero term or a placeholder term. 0x is 0 because 0 times anything is 0. So by adding 0, I'm not changing the value of this expression, just the way it looks. Now, having rewritten this, let's go find its product and its sum. Its product is 16 times negative 25. That's negative 400. What's the sum? 0. Okay, how can I write 400? Well, lots of different ways. 1 times 400, 2 times 200. 3 doesn't work. 4 times 100. 5 times 80. 6. I've run out of ideas. Let's go y equals 400 divided by x, then second table. 5 times 80. The next one is 8 times 50. After that, 10 times 40. I'll just keep scrolling down, looking for products that are a whole number times a whole number. And hopefully, Eventually, I'll find one where if I kept going, I'd be doubling back on myself. And in fact, there it is. The next one is 25 times 16. Actually, if you look at this list on your calculator, you can just do the mental addition. You can look for places where these add up to, here's 401, here's 202, here's 104, and so on. There's another caveat here, I'm afraid. We're looking for a product that's negative, so I need either a negative times a positive or a positive times a negative. In this case, I don't know if you've noticed, but it's not going to matter. There are a couple of places here where I might have taken a shortcut. Since this is a special case, and I know that I want these to add up to 0, they're going to have to be the same. It doesn't really matter whether the big number is positive and the small number is negative, because the only one that's going to work for me in this case is one where the two numbers have the same value, but one's positive and one's negative. Those are the only two that are going to add up to 0. In fact, if you saw that, if you spotted that before you started making your list, then you don't need to make the list. This is just a tool. It helps. It counts as partially showing your work, but it's not required if you can see how to get there without it. I'm going to rewrite this problem as 16x squared at the front minus 25 at the back, and in the middle, plus 20x minus 20x. And then I can continue as I've been doing all along. As I've said before, I don't normally condone getting rid of scratch work, but my screen is only so big. Now, what's common to these two terms? What goes into both 16 and 20? That would be 4. What goes into both x squared and x? That would be x. And what's left over? 4x plus 5. 4x times 4x is 16x squared, and 4x times 5 is 20x. Bring this sign down, and look for what's common between 20x and 25. That's 5. Now, this minus here is a big red flag. We have to be careful when we're undistributing. Negative 5 times what is negative 20x? I need this negative times a positive to give me this negative. And I need this negative times a to give me this negative. It's a negative times a positive that gives me a negative. So that's how I know what sign goes there. Now, what's common here and here? 4x plus 5. And what's left over? 4x minus 5. The fact that I wrote this answer with the minus factor first and the plus factor second doesn't matter. This is like saying this times that, whereas this is like saying that times this. I'm going to get the same answer. 5 times 7 is equal to 7 times 5, right? That's all that's happening here. So these two answers are equivalent. Here, I took the shortcut, and that's great if you can see it. Here, I just factored it by grouping. I had to introduce a 0 term first to make sure that I had something to split up so that I could continue. But the rest of it was just like problems we've done before. Let's do another one. Can you see this as a difference of squares? What did I have to square to get 36a squared? I have to unuse that property of exponents that said a product squared is equal to the individual factors squared. This is 6 squared times a squared. What did I have to square to get 1? 1. So this is a difference of squares. If I want to use the shortcut, I'm just going to write this as 6a plus 1 times 6a minus 1. If you're not ready for the shortcut, rewrite your problem with a 0 term. Find your product and your sum. Product is 36 times negative 1, negative 36. Product is 0. Can you tell me, without making a huge long list, what two numbers multiply to 36 but add up to 0? Well, for them to add up to 0, they're both going to have to be the same value, like 7 and negative 7, or 12 and negative 12. So which number times itself, one positive, one negative, equals 36? That would be 6. 6 times negative 6 is negative 36. 6 plus negative 6 is 0. So the two numbers I want to use when I break up my middle term are plus 6a minus 6a. It's getting crowded in here again. Now I can continue. What's common to the first two terms and the last two terms? 36 and 6 are both divisible by 6. There's one copy of a in each of the first two terms. What's left over? 6a plus 6a times what is 6a? That would be 1. Bring this sign down. What's common to 6a and 1? Nothing. Well, nothing but 1. And when you're factoring by grouping, it's a very good idea to write that 1 down. Also notice that what I'm factoring out here is a negative 1. What's left over? What do I need to multiply by negative 1 to get negative 6a? Negative 1 times 6a is negative 6a. What do I need to multiply by negative 1 to get negative 1? A negative times a positive is what's going to give me a negative. What's common here? 6a plus 1. And what's left over? 6a minus 1. 6a plus 1, 6a minus 1. Same thing. It doesn't matter which of these approaches you use. If you're ready for this and you can see it easily, that's great. This is enough to show your work. In fact, in this case, I would even say that if you can jump straight from here to here, you don't need to show this step. If you can get there, then it's clear you understand what the process is, and you don't need to show any intermediate steps. But if you don't know what's going on, if you're not absolutely sure, if you try some problems on WAMAP or in the textbook and you're not getting the right answer, then either write this intermediate step or take the long way. It won't last forever. Eventually you'll start to see these patterns for yourself. I'm really opposed to teaching shortcuts because I think it's actually better if you figure them out for yourself. The curriculum and the textbook both introduce the shortcuts, and the textbook in particular promotes it as really the only way to do this kind of problem. But it's really not. It's just a special case. Not only is there nothing wrong with doing it the long way, but if you do it the long way now, two things will happen. One is that you're much more likely to get the right answer. The other is that you'll understand the algebra behind the shortcut so that when this stuff falls away naturally, you'll have a much better grasp on this than some of your colleagues.